Welcome to this video on cooperative communication systems. Again, this will be about wireless mesh networks, and this time it's an exercise. So as you know it from other courses, we'll calculate something in this exercise which will be distance metrics, ETX as a single path metric, and EOTX as a opportunistic metric. But we'll not only talk about distance metrics, I'll also touch some coding and some things that are nearby. So this exercise used to have two parts. Now it's only one, it's shortened. This is why there's a one dot in front of everything. I just kept the numbers to be still in sync with the task sheet. Speaking of the task sheet, you will find on Opal. And I highly recommend you to try out this exercise before, try to calculate it, and if you can't solve it, at least think about how you would try to solve it. So the first part is on the expected transmission count, ETX, a single path metric. I talked about this in the two videos before, where I was lectures before where I talked about link statistics and metrics. It was this longer video split into a multitude of videos. And the ETX is a way to measure a link or path quality. We start with link quality here. And this is how it's calculated. So it's 1 divided by the success probability of a link. So let's start with the first task. The task is the setting is at first to have a link between the nodes A and B and have a packet loss probability of epsilon. So I put packet success probabilities onto the arrows very often. In this exercise we'll use packet loss probabilities denoted if you see graphs. Just beware of the difference in the exam. So again we have a node A that sends a message and a node B that receives a message. So normally in wireless media, a receiving node would acknowledge the reception of the message or the successful decoding of a message. In Wi-Fi, this is done via directly answering to the successful decoding of a message with an acknowledgement message, an ACK. If the sender does not receive the ACK, the acknowledgement packet, and the timer expires, then it would retransmit the message up to 3 times normally. But this is Wi-Fi specific again. So either the packet gets lost on the way from A to B, or the acknowledgement gets lost. But normally this acknowledgement is sent with a base rate which is probably lower than the data rate used for the packet transmission before. So in this case we have a perfect feedback link, a perfect link back from B to A, which is a bit of an exaggeration than it is in reality. Also the feedback takes no time, so A immediately knows what to do if a packet is lost or not, and so always knows how often it should transmit a message. So again, as I said, ETX is 1 divided by the success probability of the link. Here we have the error probability, so it's easy to see that the ETX of this link is 1 divided by 1 minus epsilon. So we already come to the second part of the first task. Now we have no retransmissions, and the question is how many packets are expected to be transmitted by A until 100 packets have been received by B. So no retransmissions, no backwards acknowledgement channel, no ARQ, but a continuous packet transmission from A to B over the channel with the packet loss probability epsilon. And the question is, how many packets does A have to transmit until B has 100 packets? So the ETX is the expected transmissions to have one packet successfully transmitted over the channel. So we can just multiply both sides by 100 and we get the result that 100 divided by 1 minus epsilon is the number of packets that need to be transmitted to have B having received 100 packets. So the thing is, if we have a file being transmitted, for example, so if B is interested in receiving a file from A, if random parts are missing, the download cannot be used. This is what ARQ normally is for, right? So I reduced this problem here to 5 packets to make it a bit more easy to see the differences. And so if A transmits 5 packets and we have a exemplary packet loss probability of 1/5, it could be the case that this lilac purple gets missing. The packet gets missing. So in order to have 5 packets received at B, A would have needed to transmit 7.25 packets. So of course 8 packets to be sure. But if A wants those 5 packets to be received by B and it has no ARQ mechanism, it could just choose random packets to retransmit, but would very often guess wrong in which packet to retransmit because it just doesn't know which packet went missing. So if only we had an mechanism to not send duplicates over a channel, right? I talked about this in the lectures too. So for this we can use network coding, where we mix the packets. This is visualized here in the different color encodings of the packets. Then A just transmits 8 packets over the channel. A random number gets missing, which is even 3 packets in this case. But as long as B has 5 packets, 5 different packets, which are non linear dependent, B can decode and has the 5 packets that A wanted B to know. So in this case, under some assumptions, RLNC is something like a error-free instantaneous feedback mechanism, which makes it very useful for wireless networks, and especially wireless mesh networks. So after speaking about an ETX link metric, we speak about the EOTX link metric in this case. The task is we have a node in a wireless broadcast medium, so a layer 2 broadcast medium. It's not about a routing scheme, but it's a medium where a message is received by anyone in radio range, which are the neighbors N1, N2 and N3 here, which are in radio range of A. They have each individual loss probabilities epsilon 1, 2 and 3, and we have no correlation of losses here, which is a standard assumption in opportunistic routing. So the question is, what is the expected number of retransmissions to have at least one of the neighbors receive a packet? Here we are stressing at least one of the neighbors. We don't care if it's 1 or 2 or 3. We can visualize this in this tree diagram. So at the starting point, transmission happens, then either node 1 receives the packet, and thus we do not care then about the rest of the nodes. This is already one of the interesting outcomes. If it doesn't receive the packet, then node 2 might receive the packet, which would be an interesting outcome, again for node 3. And so the only case of failure is this one, no one receives the packet. Visualized by this cloud here, and as you know from stochastic probably, we can calculate all those interesting events here via calculating the opposite event and then subtracting this from 1. So the probability for anyone receiving the packet is 1 minus the probability of no one receiving the packet, which is the same as the probability of success of the hyper edge being all outgoing edges of a node in a broadcast medium, equals 1 minus the failure probability. So the link UTX is 1 divided by the success of the hyper edge, being 1 divided by 1 minus the failure probability, epsilon times epsilon 2 times epsilon 3. The task said that the loss and or reception events are independent, so there's no correlation between losses or receptions. In reality, this might often be not the case. Let's assume we have the same setup as before, and we have another node B here, which is not in range of A. So if A starts transmitting, B might not notice. The medium contention mechanism would fail, and A and B also starts transmitting. So A and B are transmitting at the same time, which might jam the transmission for N1 and N2. And this would mean the losses are correlated then. This is just an example, but this assumption might be dangerous very often, but it's taken here for simplicity. In the second subtask, again, 100 different packets should be received. This time not by only B, but by the 3 neighbors of A. The maths here, again, is easy. We can just multiply the two sides of the equation by 100 and get the result. And we can do this because the task description mentions the keyword different packets. So if 2 neighbors receive the same packet, this is just counted as one reception event, like shown in this cloud here, where we have, and we see that even if 2 or more neighbors receive a packet, it's one packet reception. And that's why we can still use this opposite event to calculate it. 2 interesting corner cases to note here also are if there's a perfect link or a completely lossy link. The UTX shows a very interesting behavior. So if we add another neighbor, say N4, which has a completely lossy link, so no packets get through, that might be out of radio range of A, then its failure probability would be 1. So if we multiply this term here by 1, it doesn't change anything. Then the other interesting corner case, as I said, if we have one neighbor with a perfect link, then its loss probability would be 0. So say epsilon 3 is 0, then the EUTX instantly is 1, and we only have 100 packets to transmit.